I forgot to mention when we're done tonight and your brains are full and you got all sorts of additional questions that we didn't get to or you thought of after the 5 minutes, we do have a reception in the lobby where I'm pretty sure sorry, I hit the wrong button there. I'm pretty sure all of our speakers have agreed that they will stick around and you can ask them questions, get their autographs, tell them they're going to win the Nobel Prize, whatever you feel like doing with them. So we would love to have you join us there. Kristen O'Connell is her research program at the Jackson Laboratory is focused on understanding the impact of diet, body weight, and peripheral hormone signaling on neuronal excitability and plasticity in the hypothalamus and other brain regions associated with the regulation of food intake and body weight. And I pretty much did not follow any of the rules that I gave my speakers about talking in normal human language, so I apologize for that. When I asked Kristen about a favorite podcast or pop culture, she was getting stumped. So I said, how about a favorite scientist? And instantly, Rita Levi-Montalcini, who I'm going to look up as soon as we're done tonight. So.
Thank you very much. I am going to thank you all for being here. It's more important now than ever for us as scientists to communicate with you and be accessible to you. It is you for whom we work. So with that, I'm going to talk a little bit about nothing that Kate just said. I'm going to talk about cognitive aging and Alzheimer's disease, and I'm going to hope to leave you with a little bit of hope by the time I get to the end. We are all aging. The population is aging. The proportion of the population that is now diagnosed with dementia is increasing. Dementia is, of course, just a cluster of behaviors that are associated with neurodegeneration in the brain. The most common cause is Alzheimer's disease. About 80% of dementia cases are caused by AD. But there are other types of dementia, including Parkinson's, actually, which comes with a form of dementia. The biggest risk factor for dementia is age, which is why I want to talk about cognitive aging. But it's really important to understand that dementia is not a normal part of aging. While it is the biggest risk factor, it is not an inevitable consequence of growing old. The other thing I'm going to tell you that you probably already know is that there's no cure for dementia. There's no cure for Alzheimer's or any other related neurodegenerative disease. And that's in large part because, believe it or not, we still don't know what causes it. And one of the reasons for that is that the changes that happen in the brain that lead to the development of the disease begin decades before the actual symptoms emerge. So by the time someone goes to their physician complaining of cognitive impairment, the disease has been happening for years. So we don't have access to brain tissue at the point where the disease started, because that would be unethical. You're probably in your 30s or 40s when it started. Mice, therefore, remain critical to this, because that's not a consideration with mice. So if we can understand the impact of the biggest risk factor for dementia, which is age, on cognitive aging, can we identify a way to treat or prevent or even cure AD by promoting healthy aging? So I'm going to tell you about one thing we're doing in my lab. This is actually the most exciting science I've ever done in my career. I wish it wasn't happening right now, but it is. We're focused on lipids in the brain. Why lipids? Well, actually they're really cool, but that's not the only reason. Half of your brain is made of lipid. It's the second most lipid-rich organ in your body, second only to your adipose tissue. The big, most important critical point here is that many of the greatest genetic risk factors for Alzheimer's disease and Parkinson's disease are lipid-related pathways. You've probably heard of ApoE in the context of Alzheimer's. Maybe you've heard of an enzyme called GBA1. These are the single greatest genetic risk factors for these diseases, and they're related to lipid. Unfortunately, lipids are super hard to study, and we haven't really been able to do that until very, very recently. So my lab is using an advanced form of mass spectrometry. I promise that will be the last super technical word I use. That's a lie. To do what's called spatial lipidomics, which is to take a brain and look at all of the lipids and where they are and how much there is of them throughout the brain. So this is the brain from a young mouse, about 4 months old, and a mouse that's about 2 years old. And the colors represent every lipid in this brain. There's about 4,000 of them. And you can see there's a shift. with age, there's a change in the composition, distribution, and abundance of the lipids in the brain. We can use this technique not only to study lipids, but also to study proteins. And so we can look at all the proteins expressed throughout the entire brain in a technique that we have very creatively called spatial proteomics. So this is all the proteins expressed in actually these exact same brain. So it's nice we can do this in the same samples. There's about 10,000 proteins captured in this image. And it's actually kind of cool. The difference in protein is actually much more striking with age than the difference with lipid. We picked one particular protein that was most discriminant between young and old and drilled in a little more to see what it was. It's a protein called myelin basic protein. This is really exciting. You'll have to trust me because this is a lipid binding protein. So there's an intersection between lipid and protein we've never been able to investigate before. So now understanding that will give us a way to understand how these change in AD. And with that, the most important slide is the people who did this. They're brilliant. They're awesome. I just get to stand up here and talk about it.
Once again, questions? Come on up. If you could do the microphone, that would be great, please.
How important is the NIH to your work?
We cannot do this without the NIH. It will stop without the NIH.
Any other questions? Because I'm going to take over. See, smart. Don't let me do that.
So do those mice have symptoms of dementia, et cetera? Is that why you're measuring them?
The mice that I showed are actually what we just consider to be normal aging. We are now doing this in models of Alzheimer's disease. They carry familial mutations associated with early onset disease from humans. They develop pathology, including amyloid plaques, neurodegeneration, and hyperphosphorylated tau, which is more jargon than I'm supposed to use. But they do exhibit symptoms of dementia. They have cognitive impairment. They start to develop other symptoms, including sleep dysregulation, other behavioral problems.
So you said this is the most exciting work you've ever done. Why?
Because I really like the way lipids and proteins interact. It is how our brain functions. And we've never been able to do this before.
So what is it that allows you to finally do this?
This is made possible by advances in technology. The technology that we use to look at lipids and proteins has now advanced literally just in the last 2 or 3 years to the point where we don't need to know anything about what we're looking at to be able to measure it. Before, you needed to identify what you wanted to look at. That's not really all that helpful. If you're trying to discover something and you don't know what it is you're looking for, having to have some a priori knowledge of what it is not that helpful. The new technologies, which I don't want to beat a dead horse, they are because of funding, made possible because of funding from the NIH and the NSF. Without that, it wouldn't happen.
Go ahead.
Yeah, in one of your, can you hear me?
I'll repeat it. Go ahead.
In an earlier slide, it said there was a critical point that had Alzheimer's and a resilient aging and normal aging. What was that critical point?
So the question was in the earlier slide, there's a point that showed Alzheimer's and early aging, right? What's the critical point?
It's different for everyone. What that point is, at what age, point in your life where you start to exhibit changes in cognition really depends on your individual genetics, the environment you were in, educational attainment, socioeconomic status. It's different for everyone. And one of the things that we do in my lab and at JAX is create mouse models that at least capture the genetic variation, and we can start layering on some of the environmental, like diet, exercise, social interaction. Educational attainment we're still working on in mice, but give us time. We'll do it. Yep. Yep. Yep.
What happens to lipids? And raised with Alzheimer's disease?
They undergo a different change. One of the really, one of the things we didn't expect to see was that, so in the brains of the mice with AD mutations, they develop plaques, right? The amyloid plaques that are the defining symptom of the pathological hallmark of Alzheimer's. There are some lipids that specifically associate with those plaques, but it's not all of them. And we didn't expect to see that. So there are some very specific classes of lipids, and they're what are called bioactive signaling lipids. So they get metabolized and they give off small molecules that bind to other receptors and initiate signaling cascades. They seem to get tangled up with the plaques. We know that the plaque itself, amyloid itself, may not be the cause of Alzheimer's, but maybe this thing where it's kind of binding up some of these signaling lipids, maybe that's one of the things that's causing what eventually the downstream.
Hurry up.
I gather that you have to sample things and that sort of thing from human beings, so I got an 81-year-old mind, and I'd be willing to be a volunteer.
You can talk to Kristen after the reception. At the reception. Thank you. Thanks, Kristen.